70 meters a day. That's how fast one of NASA's satellites was falling out of the sky in May of 2024. The models had said 37.5 meters a day. The spacecraft, an Earth-observing satellite named Aurora, was dropping at nearly double the predicted rate, and the people responsible for tracking it found out the same way you find out your brakes are worn, by watching what happened instead of what was supposed to happen. That's the part of space weather that never makes the headline. Not the aurora, not the color, the math being wrong. And it matters this week because two clouds of solar material are currently somewhere in the 93 million miles of empty space between the sun and your front door. One left on July 26th, the other left on July 27th. Behind them, a river of fast solar wind is pouring out of a hole in the sun's atmosphere, aimed roughly at the same window of time. Three separate disturbances converging on the same few days. When solar storms stack up like that, forecasters have a word for what can happen next. They call it a cannibal. I'm going to show you exactly what left the sun, exactly what the forecast says, and exactly why the forecast is the least trustworthy part of this whole story. And I'm going to be straight with you about something most channels won't say out loud. The storm that's coming is probably going to be modest. What's interesting isn't the size, it's the shape of it. And the reason nobody on Earth can tell you the size until it's about 30 minutes away. Let's start with what we know for certain, because there's more of it than you'd think. On July 26th, at 1529 Universal Time, an active region on the sun's face labeled Active Region 4494 fired off a flare-rated M3.2. In the flare classification system, M is the second strongest category, one step below the X-class monsters. This one was moderate by solar standards and still strong enough to punch a hole in radio reception across the Americas and the Atlantic Ocean. High-frequency radio operators in that half of the world lost signal for a stretch. That's not speculation. That's a logged radio blackout, rated R1, minor on the scale, and it happened while most of the United States was going about a Sunday afternoon. Now here's what makes that flare more than a footnote. About an hour after it peaked, coronagraph cameras, the instruments that block out the sun's disk so we can see the faint material streaming off it, picked up a cloud lifting away from that same region. A coronal mass ejection. Billions of tons of magnetized plasma torn loose from the sun's atmosphere and thrown into the solar system at speeds that make our fastest spacecraft look parked. The critical detail is where on the sun it came from. Active Region 4494 was sitting near the middle of the visible disk, which means it was facing us more or less head-on. A cloud launched from the sun's edge goes sideways and misses us. A cloud launched from the center comes down the barrel. Forecasters looked at the geometry and concluded an Earth-directed component was likely. I want to be careful here, because this is where a lot of coverage gets sloppy. As of NOAA's discussion at 0030 Universal Time that night, the agency had not yet confirmed the cloud in coronagraph imagery. The United Kingdom's Met Office said the same thing, analysis pending. Confirmation came later, and the arrival estimate settled on late on July 30th. But for a full day, the largest space weather agencies on the planet were looking at the same pictures you or I could pull up on a phone and saying, honestly, we're not sure yet. If you want that kind of straight answer on what the sun is doing week to week, subscribing helps this channel tracks these systems continuously, and there's usually something moving. Then came July 27th, and the sun did something genuinely strange. At around 6 Universal Time, an enormous filament erupted. A filament is a rope of dense, relatively cool plasma suspended above the solar surface by magnetic fields, and when the support underneath it fails, the whole rope launches. This one was centered right on the sun's midline, just north of the solar equator. Tons of plasma thrown outward. And at the same moment, a huge prominence appeared over the sun's northwest horizon. A prominence is the same structure seen from the side against the blackness of space, which means a second, similar eruption was happening on the far side of the sun, the half we can't see, at almost exactly the instant the near side filament let go. Two eruptions on opposite faces of a star 865,000 miles across in sync. Solar physicists have a name for this: sympathetic eruptions. Magnetic field lines arch far above the sun's surface and connect distant regions to one another. When one structure destabilizes, the disturbance can travel along those arches and knock down another one somewhere else. It's less like two events happening and more like a single event with two exits. Watching it on the imagery, both blasts firing within the same frame, is one of those moments that reorganizes how you think about the sun. It's not a ball of fire with weather on it. It's one connected magnetic organism, and a shove in one place can tip something over on the other side of the world. Part of that filament eruption was sent our way. Forecasters expect it to deliver a faint glancing blow, arriving around August 1st. So that's the inventory. One coronal mass ejection from a moderate flare, arriving late on July 30th. One filament-driven cloud clipping us around August 1st. And a third element that most people ignore entirely. There's a large coronal hole sitting over the sun's central meridian right now in the southern hemisphere. A coronal hole is exactly what it sounds like, a region where the sun's magnetic field, instead of looping back down to the surface, opens straight out into space. Solar wind escapes through that opening at high speed, and it appears dark in ultraviolet imagery because the escaping material leaves the region cooler and thinner than its surroundings. This particular hole sits too far south to face us squarely, but part of the stream it produces is expected to reach Earth in the coming days. Fast wind, arriving in the same window as a coronal mass ejection. Hold on to that, because it's the entire reason this week is worth a video. Here's the mechanism that gives this story its name. Coronal mass ejections don't all travel at the same speed. Some crawl out at a few hundred kilometers per second, others tear away at over 2,000. When a slow cloud launches first and a fast cloud launches behind it, the fast one can catch up. Think about a snowplow on a highway in a blizzard. The plow moves slowly, but behind it there's a cleared lane packed down, easier to travel through than the untouched snow on either side. A car in that lane can move faster than it ever could on fresh powder. It gains on the plow, and if it gains enough, it doesn't pass. It hits, that's a Cannibal coronal mass ejection. The first cloud plows a channel through the ambient solar wind, thinning it out. The second cloud, traveling in that pre-cleared channel, accelerates relative to the surrounding medium and slams into the back of the first. They don't bounce apart. Plasma doesn't work that way. They compress, tangle, and merge into a single structure that carries the mass of both and a magnetic field squeezed harder than either one had on its own. The merged cloud usually hits harder, but that's not the part that makes forecasters uneasy. The part that makes them uneasy is orientation. Every coronal mass ejection carries its own magnetic field, and the single most important property of that field is whether it points north or south when it arrives. Space weather people call this component BZ. Earth's own magnetic field points north at the boundary where the two meet. When an arriving cloud's field also points north, the two fields press against each other like the same poles of two magnets, and most of the energy slides around us. When the arriving cloud's field points south, the fields link up, the door opens, energy pours into Earth's magnetosphere, and you get a geomagnetic storm. A southward BZ is the difference between a beautiful nothing and a night people remember for 20 years. Now, take two clouds with their own internal magnetic structures, ram them together at a few hundred kilometers per second, twist and compress the result across tens of millions of miles of travel, and try to predict which way the field points inside the wreckage when it gets here. You can't. Not reliably. That's the honest state of the science. The merged structure's internal field is less orderly and harder to model than a clean, single cloud. The Cannibal is not scary because it's bigger. It's scary because it's unreadable. And this is not a rare theoretical curiosity. It happened in early June of this year. Sunspot region 4455 fired 3 significant flares back to back. The clouds chased each other out into the solar system, and NOAA issued a watch for G3 strong conditions on June 4th and 5th. That was described in the coverage at the time as a cannibal event, and it pushed the aurora deep enough south that people in the northern United States were photographing it from their driveways. It happened again in May of 2024, at a scale nobody watching will forget, and I'll come back to that one because it's the most instructive event in modern space weather. It happened on the night that took down Quebec in 1989. The research published on that storm found something specific. The first cloud arrived and loaded energy into the tail of Earth's magnetic field, and then the shock front of a second cloud slamming into the magnetosphere is what appears to have triggered the release. Two clouds, one arriving into the disturbance the other had already created. That combination is why a province lost power, not the raw speed of either cloud on its own. So when forecasters see multiple ejections leaving the sun in the same few days, aimed roughly the same direction, they don't shrug. They start watching the gap between them. So let's talk about what the forecast actually says, and I want to slow down here because this is where I part company with a lot of coverage. As of today, the sun is in a lull. Over the last 24-hour observation period, it produced 6 class flares, the faintest category worth logging, down from 12 the day before. Every single one came from one region, active region 4498, sitting near the northeast limb. There are 7 numbered sunspot regions on the Earth-facing disk, including a newcomer numbered 4499, and all of them show simple magnetic configurations, alpha or beta, the arrangements least likely to produce major eruptions. Forecasters put the chance of an M-class flare through July 31st at 30%, and the chance of an X-class flare at 1%. 1%. That is a quiet sun. The geomagnetic forecast matches. Today, quiet to unsettled, with no minor storm levels expected. Tomorrow, July 30th, unsettled to active, as the July 26th cloud arrives alongside the returning high-speed stream. July 31st, unsettled to active continuing, with G1 minor geomagnetic storms possible. G1 minor, the bottom rung of a 5-rung ladder. Nobody has issued a severe storm warning. Nobody has declared a cannibal event. The 2 clouds in transit are currently modeled to arrive roughly 2 days apart, on July 30th and around August 1st, and clouds arriving 2 days apart are not merging. That spacing argues against a full cannibal scenario, and I'd be lying to you if I said otherwise. So why make this video at all? Because of the third element, because a coronal mass ejection arriving into or alongside a fast solar wind stream produces exactly the same kind of compression a cannibal does at a smaller scale. The stream catches the back of the cloud, squeezes it, and stiffens the magnetic field inside. If the field inside that compressed region happens to be pointing south when it sweeps past us, the storm outruns its forecast. That's not a hypothetical. That's the mechanism, and it's set up right now. And because of something the record shows very clearly. Before I get to it, I'm curious. Have you ever seen the aurora from somewhere it had no business being? Somewhere in the middle of the country or further south than made sense? Tell me the state and the year in the comments. Those sightings are how a lot of us first realized the sun could reach us. Here's the record. Earlier this month, on July 3rd, NOAA issued a watch for G2 conditions, moderate, following a cloud that left the sun on June 30th from an X1.1 flare. The cloud arrived around noon Universal Time on July 3rd. By the early hours of July 4th, the storm had intensified to G3 strong, 1 level above the forecast. Aurora was photographed as far south as New Mexico, magenta aurora over Northern California. The storm went 1 rung higher than the agency had predicted 3 days earlier. That's this month. Same sun, same models, same forecasters, and the outcome landed above the call. Now, go back to May of 2024, to the storm they later named for Jennifer Gannon, the space weather scientist who died that year. Between May 7th and May 11th, active region 3664 fired off multiple X-class flares and launched at least 5 earthbound coronal mass ejections. The clouds merged on the way. The storm that resulted reached G5, extreme, the top of the scale, and became the most intense geomagnetic storm in more than 20 years. The planetary K-index hit its maximum value of 9 twice. The disturbance storm time index bottomed out at minus 406 nanotesla, the largest single-day magnitude since December of 2001. Aurora was visible across most of the United States, into Mexico, and in the southern hemisphere as far as southern Africa and South America. And here's the line from the research that I keep coming back to. A formal assessment of forecast performance during that storm found that its magnitude and its duration were poorly predicted even 1 day in advance. 1 day. Not 1 week, not 1 month. 24 hours out, with the clouds already most of the way here, the models were still wrong about how big it was going to be and how long it would last. There's a physical reason for that, and once you understand it, the entire space weather business makes a different kind of sense. We can see coronal mass ejections leave the sun. We can measure their apparent speed, model their expansion, and estimate their arrival time to within about plus or minus 7 hours. What we cannot do at any distance is measure the direction of the magnetic field inside them. BZ is not visible from Earth. It is not visible from any telescope. The only way to know it is to fly through the cloud and take a reading, which is exactly what we do. There are spacecraft parked at a gravitational balance point called L1, roughly 1 million miles upstream of Earth, in the direction of the sun. When a cloud arrives, it passes those spacecraft first. They measure the magnetic field, the density, the speed, and they radio the numbers back at the speed of light. The cloud, meanwhile, keeps coming at somewhere between 400 and 2,000 kilometers per second. That gives us a warning window. And that window, the entire gap between knowing a storm's true strength and being hit by it, is somewhere between about 15 and 60 minutes. Think about that against everything else on this channel. We track hurricanes for a week before landfall. We watch volcanoes swell for months. For the one natural hazard that can reach every power grid on the daylight side of the planet at once, the meaningful warning is shorter than a lunch break. So when I tell you a storm could arrive stronger than forecast, I'm not selling you a fear. I'm describing the plumbing. And there's a wider reason this matters more than it would have 5 years ago. The sun runs on a rhythm of roughly 11 years, swinging from quiet to active and back. The current one, solar cycle 25, was expected to be mild. It wasn't. Forecasters originally put its peak at a smooth sunspot number around 115, arriving in mid-2025. Instead, activity ran ahead of the prediction, and NASA and NOAA announced the peak had already arrived in October of 2024 at a smooth number of 160.8. The sun's magnetic poles have since flipped. As of this year, we are on the downslope, heading toward the next minimum around 2030 or 2031. Here's the trap in that sentence. Downslope sounds like safe. It isn't. The Halloween storms of 2003, which produced some of the most severe space weather of the satellite era, arrived years after that cycle's peak. Declining phases produce fewer sunspots, but often more of the long-lived coronal holes that fire high-speed streams at us, and they still produce major flares from the regions that remain. A quiet week on a declining sun is a real quiet week. It's just not a guarantee about next month. What that means for you is that this window, we're in a sun with fewer spots, still throwing clouds, still opening holes, is likely to keep generating exactly this kind of week for years. Not spectacular, not nothing, repeatedly interesting. Now, let's be concrete about what a real one does, because there's a version of this topic that lives in fantasy and a version that lives in engineering reports, and only one of those is worth your time. Start with the sky, because that's the harmless part. During the May 2024 storm, aurora appeared over places that hadn't seen it in living memory. People in the American South photographed a red glow with phone cameras. That's the storm's signature. Charged particles funneled down Earth's field lines, colliding with oxygen and nitrogen high in the atmosphere, each gas glowing its own color. Then move up to orbit, where it stops being pretty. A geomagnetic storm heats the upper atmosphere. Heat makes it expand. Expansion pushes the thin outer edge of the atmosphere higher into altitudes that were effectively empty the day before. Every satellite in low Earth orbit suddenly finds itself flying through thicker air. I gave you Aura's numbers at the top, 37.5 meters a day predicted, 70 actual. Here's the rest. A satellite in one of Iridium's 6 orbital planes, flying at 780 kilometers, dropped 30 meters during the storm. Its normal decay rate is 5 meters a day. NASA's ICESat-2 at 480 kilometers was rotated by unexpected drag and went into safe hold, shutting down its instrument. 12 Starlink satellites were lost. And then the traffic problem. Roughly 5,000 Starlink spacecraft began firing thrusters autonomously a few hours into the storm, each one correcting its own orbit. Analysis afterward found that nearly half of all active satellites in low Earth orbit maneuvered at once. During the 2003 Halloween storms, about 1,000 satellites were in orbit total, and operators moved maybe 10 at a time. In 2024, thousands moved simultaneously, without human coordination, while the drag environment shifted underneath them. For days, identifying which satellites were at risk of hitting each other was close to impossible. Come down to the ground and it gets more personal. Global positioning signals travel through the ionosphere, and a storm turns that layer turbulent. During the Gannon storm, position readings were thrown off by hundreds of feet, and in some American states, the disruption lasted up to 2 days. It landed in the first half of May planting season across the Corn Belt. Modern planters steer themselves by satellite to accuracies measured in inches. When the signal wandered, machines stopped or went offline. Terry Griffin, an agricultural economist at Kansas State University, presented the estimate. Corn farmers lost around $500 million. He described that figure as conservative. $500 million of American agriculture gone because of the magnetic orientation of a cloud of gas that left the sun 3 days earlier. No wind, no rain, no warning that meant anything. And then there's the grid, which brings us to the event every space weather engineer measures the others against. March 13th, 1989, 2:44 in the morning, Eastern Time. A surge of electric current, induced in the bedrock of the Canadian Shield by a violently fluctuating magnetic field, found an easier path through Hydro-Quebec's long transmission lines than through the rock itself. It tripped a capacitor at the James Bay complex. Protective systems cascaded. In under 90 seconds, 21 gigawatts of supply went offline and the entire provincial grid collapsed. 6 million people lost power. Outside, it was around minus 15 Celsius. Most of them were asleep and woke into a cold, dark house with no explanation. Service returned for most customers after about 9 hours. Some industrial sites waited days. And here's the detail that engineers consider more important than the blackout itself. 1,500 kilometers to the south, at the Salem Nuclear Station in New Jersey, the same storm destroyed a large transformer. No blackout, no headline, no drama, just a critical piece of equipment quietly cooked from the inside by currents it was never designed to carry. More than 200 grid faults were logged across the United States that night. Operators worked around all of them. David Boteller, who heads the Space Weather Group at Natural Resources Canada, has described March 1989 as the biggest geomagnetic storm of the space age and the reference case for understanding how solar activity brings down electrical systems. Which brings me to the part where I have to take something away from you. You've probably seen the version of this story that ends with the internet gone for a year and civilization on its knees. Some of the raw ingredients in that story are real. Extra high voltage transformers are built by a small number of factories worldwide. They're custom units, and replacing a large one can take a very long time. Undersea cable repeaters and continent-scale transmission systems are exposed in ways that are documented in the engineering literature, not invented for clicks. But the leap from those facts to collapse skips everything that happened after 1989. Hydro-Quebec spent roughly $2 billion over 6 years hardening its system series capacitors, higher trip thresholds, recalibrated protection, better monitoring. North American and Northern European utilities built programs specifically to manage geomagnetically induced currents. Grid operators now receive space weather alerts and reduce loading in advance. The system that failed in 90 seconds in 1989 is not the system we have today. And more to the point, none of that is on the table this week. A G1 storm does not threaten a transformer. It gives high-latitude operators a mild fluctuation to watch, degrades some radio propagation, and if the timing works out, puts a green smear on the northern horizon. The honest headline for the next few days is this: a modest storm with an unusually cluttered setup arriving with a wider than normal margin of error. That's the truth, and I think it's more interesting than the cartoon, because the margin of error is the story. So, what should you actually watch? And who should care? If you're in the northern tier of the United States, Washington, Idaho, Montana, the Dakotas, Minnesota, Wisconsin, Michigan, upstate New York, northern New England. The nights of July 30th and 31st are worth a look at the northern horizon after full dark. Get away from streetlights. Let your eyes adjust for 20 minutes. And use your phone camera even if you see nothing, because modern sensors pick up aurora that's below the threshold of human night vision. The number to track is KP, the planetary index, on a scale from 0 to 9. It's been sitting between 1 and 3. KP5 means minor storm conditions have arrived. KP6 means moderate. NOAA publishes it live, and it updates far faster than any news article. If you fly, especially on polar routes, high-frequency radio degradation is the operational issue, and airlines already plan for it. If you use precision satellite guidance for farm work, survey work, or drone operations, be aware that position error can climb during disturbed periods, and this window overlaps a working week. If you operate high-frequency radio, expect fading at high latitudes. For everyone else, the correct response is interest, not preparation. This is not a storm to stock water for. What it's worth doing, in the abstract, is knowing that your household's tolerance for a 9-hour power outage, a flashlight, a way to charge a phone, a plan for heat or cooling is the same tolerance that covers ice storms, hurricanes, and grid faults. Space weather doesn't need its own kit. It needs the one you should already have for the weather that reaches your house every year. Here's what I'll be watching, and what will tell us how this ends. First, the arrival signature late on July 30th. When the cloud hits, spacecraft at L1 will register a jump in solar wind speed and a spike in total magnetic field strength. That jump is the starting gun. Second, and everything hangs on this, whether BZ turns south and stays there. A sustained southward field is the condition that turns an arrival into a storm. Brief southward wobbles do very little. Hours of sustained southward field is what pushed May 2024 to the top of the scale. Third, whether the coronal hole stream arrives at the same time and compresses the back of the cloud. That's the compression scenario I described, the small-scale cousin of a cannibal, and the single most likely path to this event overrunning its forecast. Fourth, around August 1st, the glancing blow from the July 27th filament, which forecasters expect to be faint. And fifth, the thing beyond this week. Active region 4498 is rotating into better view. It's the only region on the disk producing flares right now, and it currently shows a simple beta magnetic configuration. But it's still too close to the sun's edge for a full reading of its magnetic structure. Over the next few days, it turns toward us, and forecasters will get their first clean look at what it's carrying. If it carries more complexity than it appears to, the quiet week ends. That's the sequence: an arrival, a magnetic coin flip, a stream that may or may not squeeze it, a graze, and a sunspot rotating into the light with its cards face down. Subscribe and turn on the bell if you want the follow-up, because I'll be posting the moment those L1 readings come in on July 30th, whether this thing lands as forecast or does what it did on the 4th of July and goes a level higher than anyone said it would. The sun turns about once every 27 days. Whatever is on the far side right now is coming around.